All right, couple of announcements. First of all, we're going to do a demo in class on Wednesday and Friday with some software called HECRAS. And it's free software. It's put out by the Army Corps of Engineers. You just do a Google search to find it. And what I'd like you to do is install it on your computer before class on Wednesday. So download HECRAS. It'll take you right to the location. It's relatively small. 200 megabytes. So please download and install that. It allows us to find water depths with gradually varying flow. So it's kind of, rather than using hand calculations or spreadsheets when you're doing real world river analysis, then HECRAS would be one of the really powerful tools that's available for that. So please install that on your computer before class on Wednesday. I think we'll get started on Wednesday towards the end of class, and then we'll spend the entirety on Friday going through an example or two. So then the next thing that you actually have to submit is on Friday of this week, where your design project final report is due before class. And remember that there's a video where I talked at length on what the formatting of that report and the other files should look like. And then I'm also making available an optional final exam review session if you'd like to attend that on Friday at 2 p.m. I looked over the schedules of everybody in the class, and it was either 8 a.m. or 2 p.m. on a Friday, and I opted for 2 p.m. I'm not a morning person. Now, I'm not going to give any hints about the exam in that review session. I'm not going to be like steering you towards certain things that you ought to study because that's what's going to be on the test. I won't have written the exam by then. The way I think that's going to work is my vision for the review session is I'm going to go through the equation sheet and we'll talk about what each formula is used for. We're going to look over the schedule of the semester and just briefly review each of the topics that we've discussed. And then I also have a database of previous quizzes, not only the quizzes that you've seen, but quizzes from many other semesters. And I might just randomly pull up questions from those, and then even if we don't necessarily solve them, because I'm just intending for this to be about an hour approximately, we just kind of talk about which formula applies there, what kind of a problem it is, so that you have more practice just identifying a problem type and then knowing which path to start going down. So that optional review session is Friday at 2. And then next week, on Friday, May 2nd, you'll have your last assignment. Homework 13 is posted now. It's only 2 problems. It's not especially lengthy. One of them is a standard step method problem, which we're going to be talking about today. So you could do the larger of the 2 problems after today's class, I think. And then the other problem on homework 13 is related to sewer analysis and design, and we'll get to that next week after we do the HECRAS stuff. So that's kind of a glimpse of where things are headed for the rest of the semester. Does anybody have any questions related to these announcements? All right, so standard step method is just another tool that we have for situations where the direct step method maybe wouldn't apply. And when we were working the direct step method, what we applied it for was channels where the width and shape wasn't changing as we went upstream or downstream across a backwater curve, trying to find out, for example, how long would it take before we got from some pooled water depth back to the normal water depth where conditions were steady and uniform. And so the big limitation here is that it's assuming that the cross-sectional shape is the same. Now, the standard step method doesn't make that same assumption, but we can only apply it from one segment to the next. We can't do it across an entire string of segments. We could just do one piece at a time. So if we were going to be applying the standard step method where the shape of the channel was changing and we had a really long backwater curve like this, then we may have to apply the method on separate spreadsheets multiple times. And that's kind of why you're going to see that the HECRAS software is so beneficial is it uses the standard step method. It's able to overcome changes in channel geometry, and it's also, you're able to lay out what the entire stream is for a very long distance, whereas in the method we're going to do today, we'll just be doing a single jump at a time, just one segment, and it's still a pretty detailed process to do that one segment. So we've talked about the limitations of the direct step method, and the standard step method's advantage over that is it can be used regardless of the shape and whether it's constant or changing. Now, one of the things we have to be sensitive to is that when we look through the book, the way it describes the standard step method, it's using the number 1 and the number 2 a little bit differently than everywhere else in the book. Generally, everywhere else in the book, 1 means upstream and 2 means downstream. And in the context of the standard step method, instead what that means, 1 is the location where you know the depth and you know the channel conditions, you know the elevation above the datum. It's just where you know everything is location 1. And then location 2 is where you're trying to find out the water depth. And so it may be upstream or downstream depending on whether you've got supercritical or subcritical conditions. But I want to just give you this alert that here in this equation, where it says the water surface elevation at 1 plus the velocity head at 1 and the head loss, that should already kind of seem strange to you that head loss is on the left-hand side of the equation, because every other time we've been looking at the energy equation in previous kind of formulas, the head loss would be on the right-hand side, because in all those previous assumptions, 1 means upstream and 2 means downstream. So here, this is a subcritical condition. If we look at this, this sketch here, this is subcritical flow. And so when we have subcritical flow, what we would do is we would work upstream towards some unknown location number 2. So 1 is where we know the water depth and we know the elevation above the datum and we know the velocity head. But then the head loss would be on the on the left-hand side of the equation here, because 1 is downstream, and head loss is always lost as you're going downstream. So the amount of energy at 1 is less than the amount of energy at 2 in the amount of the head loss that was experienced between the 2 points. So just keep that in mind. 1 means known, 2 means unknown. So the method that we're going to work through with that spreadsheet template that I gave you is we have to begin with a guess of what is the depth at location 2. Remember, location 2 is where we don't know the depth. So we're starting at 1 where we know the depth, and so we're getting back to one of these old tricks that we used to use on several previous problems, where we didn't exactly know maybe what the flow rate was, so we guessed a flow rate, and then we saw, is that true? Do we need to make a change? And if so, maybe the method gives us some guidance on whether to increase or decrease our previous guess, and maybe even by how much if we're lucky. So similar thing here. We're going to assume a water surface elevation. Now, water surface, from the sketch, you can see that that includes 2 things. Water surface is Z, so that's the elevation from the datum to the bottom of the channel, and then Y, so that's the flow depth. So water surface, let me write this on the board, it's just water surface is Y plus Z. It's that simple. So we're going to have to guess at 2 what it is, and then based on that guess, we'll compute an observed head loss. And so the observed head loss is just the specific energy at 2 minus the specific energy at 1. And then we'll come up with a calculated head loss, which is based on the slope of the midpoint, slope of the energy grade line at the midpoint multiplied by the segment length between the 2 points. And then C here is a coefficient that accounts for energy loss due to the change in shape. because in the standard step method, the channel's getting wider or narrower, or maybe it's transitioning from a rectangle to a trapezoid, and there's just going to be some energy loss associated with that. So C is a coefficient that we use to multiply by the absolute value of the difference of the velocity heads. And then, of course, remember, we can estimate the slope of the energy grade line with Manning's equation. So this Manning's equation, here it's written in terms of SI. If it's in terms of traditional units, then there's the 1.49 coefficient involved. And we will have an example today where that's the case, where we're working in traditional units. But the point is, we use Manning's equation to estimate what is the slope of the energy grade line at the midpoint. So we find the observed and the calculated, and if they're not the same, then that tells us our guess wasn't correct. Our guess of what is the water surface elevation at 2. And so if they don't match, then we'll calculate an updated water surface elevation. And the way that we know the updated water surface elevation is by looking at the calculated head loss and the previous velocity at 2 that's implied by the depth of the water surface at 2. And then kind of updating it by averaging your previous water surface assumption and some new calculated water surface depth. And then we just keep cycling this process over and over until the observed and the calculated head loss are equal. And when they are, we assume that our solution is converged and we've got the correct water surface elevation at location 2, where's the unknown. So that's the method that is built into the spreadsheet template we're going to use today. Any questions so far about the purpose of the standard step method or the calculations? Anything so far? All right. So we're going to work with this example. You can see we're in traditional units. So here at section 1, that's where we know everything. It's a trapezoidal shape. The bottom of the channel is 5 feet above our elevation datum. So here invert, the word invert means the bottom of the channel. So the bottom of the channel is at an elevation of 5, where datum is where we're saying 0, it's our 0 point for elevation. And the water depth is 5 feet. And so the water surface at 1 would be the delta Z is 5 plus the Y is 5. So the water surface at 1 is 10 feet. You can see it's got 2-to-1 side slopes here. So 2 is the horizontal component, 1 is the vertical component. And then upstream, basically what's happening is, you see how the bottom width is 25 feet? It's also, the bottom width is 25 feet, 1,000 feet upstream, but what it's doing in between section 1 and section 2 is that the sides of the trapezoid are gradually coming up. And we assume that that's happening linearly, where if we went halfway between section 1 and section 2, instead of 1-to-2 side slopes, it would be 1-to-1 side slopes. And then it's gradually becoming so that it's vertical side slopes. And we want to know, how is that affecting the water depth? The fact that, number one, the channel is changing, but then despite that, there's also some obstruction that is causing gradually varied flow. So this is going to take care of both of those things, the gradually varying flow that could be independent of the channel geometry changing, but then also the effect of the channel geometry where the side slopes are coming up as we go upstream. So just one other point, remember section 1 is where we know things, and it's downstream. Section 2, where we want to find the depth, is upstream. Look at the invert elevation here where it says the invert is 7. I mean, that kind of tells us that the water's coming from 2 towards 1, because section 2, the bottom of the channel is higher. So the water couldn't possibly be going from section 1 towards section 2, because section 2 is at a higher elevation. So the water's going downhill from 2, So let me just draw this on the board. This is exaggerating the slope here, but here's section 2, and here's section 1. At section 1, we know that the water depth is 5 feet. And then it's 5 feet from the datum up to the bottom of the channel. Whereas at section 2, it's 7 feet. And we want to find out what is the depth at location 2. How deep is it? Now, this is just a cross-sectional view here. We can't see the effect of, the water starts at 2, it's rectangular, and then it's getting wider as it goes downstream. So it started as a rectangular channel. If we think about the water flowing downstream, then we can think about these sides gradually kind of swinging down. We know the flow rate is 1,000 CFS. We've got a roughness value here, 0.05. And then the expansion coefficient is just related to the energy that's lost as turbulence is kind of induced as the channel's getting wider downstream. Okay, so let's start off with just some hand calculations. And we want to know what is the normal depth and the critical depth at location 1. I think it's always a good habit to classify the water surface profile. So this is traditional units. So to find the normal depth, we're going to use Manning's equation in terms of Q equals 1.49 times the area to the 5/3 slope to the 1/2 divided by n, and then wetted perimeter to the 2/3 power. Okay, and for a trapezoid like this, then the area is going to be 25 times y and adding 2 times y squared. Okay, so this is trapezoid with side slopes of 2 to 1. So that's the area. Then the wetted perimeter, P is 25 plus 4.472 times y. So substitute that into Manning's equation and find out what's the normal depth. We want to know, first of all, normal depth from Manning's equation. But then we also want to know the critical depth. And at section 1, where we know the conditions, it's not rectangular. So we can't use what we usually do for finding the critical depth. Normally for critical depth, we're finding Q squared divided by G to the 1/3 power. That doesn't apply if you've got a trapezoidal channel, because there's no such thing really as flow per unit width if you've got a trapezoid with side slopes. And so to find the critical depth, instead what we'd use is the Froude number. So Froude number formula, it says the Froude number is Q squared times the top width, capital B, divided by G, times area to the 3rd power, and all of that is to the 1/2. So from that we can find the critical depth, where the top width here is going to be so when we want to find the critical conditions, B is 25 plus 4 times YC, and then the area is 25 YC plus 2 times YC squared. All right. So I'm going to pause for a moment, give you a chance to calculate normal depth, and then number 2, critical depth. And the reason why we're doing it is to classify the water surface profile. Always a good habit when you're doing gradually varying flow problems, because it gives you an idea if the water should be deeper or shallower in the direction that things are changing. All right, we're going to need to know the slope if we're utilizing Manning's equation, and here we know that if it's 1,000 feet apart, you're losing 2 feet of elevation from section 2 by the time you get to section 1, because it goes from an invert elevation of 7 feet down to an invert elevation of 5 feet. So the slope of the water of the channel is 2-foot drop out of 1,000 feet of length, so 0.002. So, Manning's equation is what we use to find the normal depth. We find that that's 6.848. So the normal depth, 6.848. The critical depth we solve for here, since it's trapezoidal, just in terms of the full Froude number equation. Get that the critical depth is 3.346 feet. And so then the first part of classifying the water surface profile is comparing the normal depth to the critical depth, because we want to know, is it mild or steep? And here, normal depth is more than critical depth, so that means it's an M, mild. And then which zone we're in, we compare the actual given water depth of 5 feet to the critical and the normal. So if we go back into our water surface profile sketches that shows the 3 different zones. So we've got a mild slope because normal is greater than critical, but then our actual flow depth is between the two. So that puts us into zone 2. So this is an M2 profile. And in an M2 profile, we would expect to see that if you go upstream, the water's deeper. And that's what we're doing in this example. We're working from the location here where we know the depth is 5 feet. The question is, if we move upstream, is it going to be shallower or deeper? And this being an M2 profile suggests that it's going to be deeper upstream. Now, we could sometimes have surprises based on the fact that the channel geometry is changing. And so the standard step method takes into account the kind of normal inclinations or behavior that you'd see based on the profile type, but then also the change of the geometry. So in this case, we've got an M2 profile at location 1 where we know everything. So this is where we're going to switch over to using that template file that I put onto Blackboard for you. Is we want to go through this Excel spreadsheet and try and figure out what actually is that depth upstream. So template files, standard step, student start. That's it. Okay, we're going to start off by just putting in some of the parameters that we already know. Here at the top, like the flow rate is 1,000 CFS. The end value of the channel, just based on what it's made out of, is 0.05. Z1, that's the distance from the datum to the invert at section 1 is 5 feet, 7 feet for location 2. The expansion coefficient was given in the problem statement to be 0.3. And then this is 1,000 feet apart, so L is 1,000 feet. All right, so here at location 1, we're going to begin by just putting all the things that we know. We know the flow depth is 5 feet. We know that the area for a rectangular section, like it is at 1, the area is just the width of the bottom. Oh, no, I'm sorry. This is trapezoidal at location 1. So the area is going to be this formula, 25 times y plus 2y squared. So equals 25 times y plus 2 times y, which is cell A30 squared. All right, 175 square feet. The velocity of the flow is just the q, which I'll anchor the reference because I'm going to be dragging this down from multiple rows. So q divided by the area that we've just calculated. Wetted perimeter, here's the formula on the whiteboard, 25 plus 4.472 times y. So that's just, the geometry table 10.1 where it's got all of the different properties for, calculating W from T, where T is the side slope. We calculate W, and then from that we get the wetted perimeter. That's where that came from. So 25 plus 4.472 times the depth. Okay, so the wetted perimeter is 47.36. The definition of hydraulic radius is area divided by wetted perimeter. And then the specific energy at 1 is going to be the velocity head plus the depth of the water. So the water depth, y, plus the velocity head. So it's v squared divided by 2 times g. Remember, here we've got traditional units, so g is 32.2. Okay, so we've got the specific energy. Let's actually make that total energy, not specific energy. So add in the Z1 as well. So the depth, water, the depth, the velocity head, plus the elevation. Okay, so this is total energy. All right, now the slope of the energy grade line at section 1, we're using Manning's equation for that. Here's Manning's equation written in terms of solving for S sub F, and we've got the 1.49 because it's traditional units, so it is N times Q, reference, anchor the reference to N with the F4 button, times Q, again, anchor the reference, divided by 1.49 times the area times the hydraulic radius to the power of 2/3. And close parentheses for the denominator, close parentheses for the entire expression, and raise it to the power of 2. Okay, so we've got Manning's equation rearranged to give us the slope of the energy grade line at the downstream section 1 where we know things. Oh, there must be an error there someplace. Let's see. Q times the slope. 1.49.
You added it in.
Oh, thank you. Yeah, good catch. Multiply. Okay, that's more like it. 0.00644. Okay, so now we assume some water depth at location 2. We don't know. A good guess would be that it's deeper. Remember, we found that it's an M2 profile, which suggests upstream it's going to be deeper based on this shape. So let's just say 5.1 feet deep. Okay, so if it is 5.1 feet, then the water surface elevation would be the depth of 5.1 plus the delta Z, which is 7 feet. Anchor that reference up there to the top for the 7. Okay, so if the depth is 5.1, then the water surface elevation is 12.1. The area, it's rectangular at section 2, so the area is easy to calculate. It's just 25 feet wide times whatever the depth is. So that's how we get the area at 2. Then the velocity would be the flow rate divided by the area. So Q, anchor the reference, divided by A. Okay, so 7.8 feet per second. The wetted perimeter at location 2, this is rectangular, so the wetted perimeter is the bottom width plus 2 times the depth, because that's where the water is going to be touching whatever material this is. So it is 25, the bottom width, plus 2 times the depth that we've just assumed here of 5.1. So that gives us the wetted perimeter 35.2. Hydraulic radius is defined as the area divided by the wetted perimeter. Okay, so 3.6. E here is going to be total energy, so total energy. So that is the depth plus the delta Z. I guess we could just make it the water surface because the water surface is delta Z plus the depth. So for total energy, let's make it water surface plus the velocity head. So now V squared divided by 2 times 32.2. So the total energy at location 2, it's the water surface plus the velocity head, 13.055. And then the slope of the energy grade line at location 2, again we're using Manning's equation for that. So it will be the n value times the flow rate divided by 1.49, because we're still in traditional units, times the area of section 2 times the hydraulic radius of section 2 to the power of 2/3. And then close parentheses for the 2/3, close parentheses for the denominator, close parentheses for the whole expression, and take it to the power of 2. So the slope of the energy grade line at location 2 is 0.01245. Any questions so far? Is there anything that I need to go back and illustrate again for what I had typed in? Okay, the observed head loss that this is talking about, observed head loss is just E2 minus E1. So observed head loss is E2 minus E1. 2.548 is the change in of total energy between the 2 points. And now SF bar, we're going to calculate, that's just the average of the two, because here we've got SF1 and SF2. So we're going to assume that the slope of the energy grade line at the midpoint is just the average of them. So energy grade line slope at 1 plus energy grade line slope at 2 divided by 2. Is there anything I need to go back over or explain another time?
Can I see the S-bar equation one more time?
Mm-hmm. It's just the average of at 1 and 2. So add them together and divide by 2. What else? Are there other things I also need to show? Okay, so here for the calculated head loss, we're going to use this SF bar that we just calculated. Okay, so calculated head loss is this SF bar times the length of the section, 1,000 feet. It's a strange thing with Excel. Sometimes when I'm zoomed in more than 100%, the cells are in the wrong place. So no matter where I click, let's take it back to 100%, I guess. All right, so equals, it's just, it's the clumsiest I've ever been on a spreadsheet. No matter where I click, it's taking me to the wrong spot. All right, so this slope of the energy grade line we just calculated, multiplied by the length. So here's the length. Anchor that reference to the length, but not to the average energy grade line slope. And then plus the C value. So C value is here, 0.03, anchor that. And if I was planning ahead, I would have made a separate column just for the velocity head. Instead, I'll have to type those formulas in. So we want to multiply that by absolute value of the velocity head at 2. So this is velocity squared divided by 2 divided by 32.2 minus the same thing at 1. So, oh, that was it. No, yeah, it was at 2. C K. K takes me to V2. So velocity at 2 squared divided by 2g minus the velocity at 1 squared divided by 2 divided by g, close parentheses. All right. So the calculated head loss 9.579, and those aren't the same. The observed and the calculated aren't the same, so that tells me that my initial guess isn't good. So the calculated water surface is going to be using this formula here. So the water surface at 1, which is the depth and the z value. So have the water depth at 1 plus z1, anchor that reference up to the top there, since that's not ever going to be changing. So that gives us water surface at 1 plus the velocity head at 1. So v1 squared divided by 2 divided by 32.2 plus the head loss that's calculated. So the calculated head loss is in cell T30. So I'll type in here T30 and then subtract out the velocity head at 2. So minus the velocity head at 2, where that is going to be K30 squared divided by 2 divided by 32.2. So the water surface that's calculated based on all of these assumptions about what the water depth would be is 19.13. So then the updated would be the previously calculated water surface, so this water surface plus this new one that we've just calculated, and then divide it by 2. So it's the average. Kind of split the difference between our earlier guess and our newer guess. So this is saying 19.13 versus, oh, here's the water surface at 2 is 12.1. So the average between the two is this, and then that's what we're going to use for our next guess of the depth at 2. So our next depth, this is going to be the last thing we'll do for today, and then we're going to save it. So we want to start the next round of iteration. It's going to be this minus Z2. So this is saying our first guess was 5.1. That's too low. Let's try 8.62 with our next round. And it's just based on the fact that this updated water surface is some depth and the Z2. So we get the depth by subtracting Z2 from the updated water surface. All right, it's 1:50. We're out of time. So save this. And when we get together on Wednesday, we're going to pick back up where we left off and continue the example.